Good morning and welcome you all to this session of the course on fluid machines. Now, today we will be discussing a reciprocating pump. At the beginning of this course, we discussed that there is basically two types of fluid machines. One is rotodynamic machine, another is positive displacement machines, and these two categories are differentiated on the basis of their principle of operations. In a rotodynamic machines, the energy transfer between the machine rotor and the fluid takes place by the hydrodynamic action between a continuous stream of fluid flowing through the rotor blade passages. While in a reciprocating machines, this energy transfer takes place by changing the volume of a certain mass of fluid content within the machine by the physical displacement of one of its boundaries. Now, reciprocating pump, where the fluid pressure is increased, the energy is manifested in terms of rise in static pressure, is made by the principle of positive displacement. Now, usually in practice, the reciprocating pump looks like that. It basically consists of a piston or plunger moving in a cylinder, executing a reciprocating motion in a tightly fitting cylinder. This is cylinder, this is the piston or plunger, and this movement is being executed by a connecting rod and a crank, which is connected to the crankshaft, final output shaft, input shaft here, where the energy is given. Now, you see the operation is like that. When this piston moves this side outward of the cylinder, then there is a fall in pressure of the liquid, and due to this the liquid from the sump, that is lower reservoir, comes in to the cylinder, and there is an inlet valve which automatically opens because of the reduction in pressure. That means, this opening is automatically done by change in the fluid pressure during the suction stroke. Now, at the end of the suction stroke, when the piston reaches its outer dead center, this is known as dead center at the two extreme point, inner and outer, then what happens? The piston again, while coming inward, changes the pressure in the fluid, and during that operation, that means this stroke from outward to inner direction, the movement of the piston, this valve is closed and this valve gets open, that is outlet valve, because of the high pressure created here by the movement of the piston, which pushes the liquid and creates a high pressure. And then during the stroke towards inner dead center position or inward, the fluid at high pressure is being discharged through this pipe. Now, this is the suction lift, this is known as HS, which is the height of the center of the pump's cylinder from the lower head reservoir, and this height, that height from the center of the pump cylinder to the discharge point, the overhead reservoir or the discharge point vertically above, is known as the HD, that is the delivery lift, this is HD. So, a pump delivers a head is equal to HS plus HD, which is the static lift, as we have already seen in centrifugal pump. Now, here you see this, as the piston moves here, piston exerts a pressure. Now, at any instant, if you consider the piston pressure is P, which is exerted on the liquid, instantaneous pressure, then we can write that the small amount of work that is being transferred to the fluid or done by the piston with that pressure P, if we consider at that instant piston momentarily in equilibrium under that pressure, which is again acting on the piston on this side. This is the pressure acting on the piston. Then piston exerts the pressure on the liquid, pressure acting on the piston. And if we consider a cross-sectional area of the cylinder A, and for a infinite small displacement of the piston dx, that means the work which equals to integral del W is nothing but integral, this A dx can be written as elemental volume. That means, it is integral PdV. It is almost similar to this PdV work in thermodynamics in consideration of the piston at local and instantaneous thermodynamic equilibrium. Though piston is not at all in thermodynamic equilibrium, it has got acceleration, deceleration, and the pressure is changing. So, instantaneous pressure, by which you can express the work done as an integral of PdV. That means, it is the change in the pressure in the liquid in the cylinder and the liquid volume in the cylinder because of the piston motion is responsible for the energy transfer and can be expressed like that. So, with this in mind, if we now try to draw a pressure volume diagram for this cylinder, that means this side get volume and this side if we write the absolute pressure, then we get a diagram like that. Let me first draw, then I will explain you. Let me first draw, then I will explain you. The ideal pressure volume diagram, like a cycle diagram in thermodynamics for a thermodynamic cycle, looks like a rectangle ABCD. What is this? This is the atmospheric pressure line and this is our suction lift HS, that is the vertical height of the pump cylinder from the lower reservoir. Now, in the ideal case, the pressure, if we neglect the velocity and acceleration of the fluid in the piston and in the pipeline, then we expect in an ideal case that the suction pressure should be sufficient enough to lift this water by height S. So, therefore, suction pressure head will be equal to that of the HS. Okay. So, suction pressure head will be equal to that of the HS and in an ideal case it will be constant throughout the process as the piston moves in this direction. It is similar to, if you recollect in thermodynamics, is the suction process of an air standard cycle like Otto cycle or diesel cycle. So, it is a constant pressure suction. So, this is absolute pressure head rather. When I express this in terms of HS, this is absolute pressure head, So, therefore, this is HS below the atmospheric pressure. A to B is the suction. Now, at the end of the suction, the piston pushes the liquid. Now, if we consider liquid to be ideally incompressible, fully incompressible, the property of incompressible fluid is that it gets pressurized instantaneously without changing in volume. Why? This is because that if the piston pushes it, a pressure wave is generated which actually transmitted upstream to pressurize the entire fluid. In an 100% incompressible fluid, in an ideally incompressible fluid, this travelling of the pressure wave in the fluid medium is almost infinity, is very, very high. So, therefore, instantaneously it is sensed upstream, which means that any pushing here resulting in a rise in pressure will be sensed by the entire fluid in this cylinder, and that is the property of the incompressible fluid. The fluid is perfectly incompressible, fully incompressible, then we get, that means the modulus of elasticity is infinitely high. So, that this is immediately sensed. So, this is considered to be an instantaneous pressure rise without any change of volume, and that is why the C is there. So, therefore, this is the direction of suction, this is suction, and again at the delivery, this is the delivery line, delivery direction. So, therefore, pressure is raised to delivery pressure, that is equal to HD, that is the height, that is the delivery lift, HD. So, this is HD. So, therefore, one can say that this is HD and the total is HS plus HD, is the total lift of the static lift of the pump. And similarly, at the end of the delivery stroke, when the piston comes the inner dead position, then innermost position in the cylinder, then immediately at the start of his stroke or reciprocating motion outwards, that means towards the outer dead center position, the pressure falls instantaneously to the suction. So, this is an ideal diagram rectangle in case of PV. Now, here this diagram is changed because of the fact that when piston executes the reciprocating motion, it has acceleration and deceleration. Piston executes a motion through this connecting rod, and crank mechanism executes an accelerating decelerating motion. In an ideal case where the connecting rod is much longer than the crank, we can consider this as a simple harmonic motion. So, it executes a simple harmonic motion where there is both acceleration and deceleration. In that case, what happens? The piston pressure within the cylinder varies in suction and in delivery stroke. Now, suction stroke, what happens at the beginning of the suction stroke, the fluid has an acceleration. Fluid has got 0 velocity here at the inner dead center position. When it starts from the inner dead center position, the velocity increases, and not only velocity, acceleration also decreases. The velocity increases, but acceleration decreases, but there is a sharp acceleration. So, acceleration starts at the beginning. So, because of this acceleration, the suction head required will be more than that of the static lift in consideration of the acceleration head. That is known as acceleration head. That means an extra force has to be given, an extra energy has to be created to draw the fluid with acceleration. And this acceleration in the pipeline will be more than that in the cylinder because of the difference in cross sectional area. Now, liquid will be moving with the same velocity and acceleration of that of the piston in the cylinder, and at any instant of time the liquid velocity in the cylinder, velocity and acceleration in the cylinder, and the liquid velocity and acceleration in the pipeline will be related to their cross sectional area. So, the liquid velocity and acceleration in the pipeline will be more than that in the cylinder because of lower cross sectional area in the of the pipeline than that of the cylinder. So, therefore, finally, the liquid velocity and acceleration both in piston and the in cylinder and the pipeline depends upon the piston velocity. So, initially it provides an acceleration. So, more head will be required to draw this, and acceleration ultimately reduces, as I told, it starts at the beginning, but ultimately there is an increase in velocity, the acceleration reduces, and in the middle of the stroke, if we consider this to be executing a simple harmonic motion, velocity will be maximum and the acceleration will be 0. And then acceleration switches of its direction. That means it goes on retardation. That means velocity from a maximum value goes on decreasing and comes to 0. When again acceleration becomes minus, a maximum with a minus sign, that means deceleration. So, the rest part is deceleration, where a higher pressure is needed in the cylinder during the suction stroke. So, to take care of initial first part acceleration and subsequently the deceleration, the head requirement at the in the suction stroke can be modified like this. Can be modified like this, and I give this nomenclature as EF. That means, in consideration of a simple harmonic motion, this will be a straight line where E is the minimum pressure in the cylinder, which is lower than the static head Hs. This is the suction head or suction lift Hs. This is the point where to take care of an acceleration, initial acceleration, that additional head is required. At the same time, because of deceleration here, the velocity is maximum and acceleration is 0. The pressure needed is less, so that ultimately it ends here. So, finally, EF is the modification of this ideal suction stroke AB in consideration of piston acceleration and deceleration. Now, along with that, there are viscous losses in the pipeline and also in the cylinder. So, these viscous losses, that means the loss of energy due to fluid friction, this has to be also surmounted by the head in the suction side. So, this losses is proportional to velocity. as you know, the viscous losses is always proportional to square of the velocity. So, at this point at the dead center, that is the inner dead center position at the start of the suction stroke, this is 0. Again at the end this is 0, here the velocity is maximum. So, loss is maximum here. So, if you take care of this parabolic law of the losses and its variation with the flow velocity, which is 0 0 here at the two dead center and being maximum at the middle, we can modify this curve like this ELF. So, therefore, you see the ideal suction stroke AB is finally modified as ELF in the suction stroke in consideration of the inertia of the piston, that means is acceleration and deceleration, and in consideration of a simple harmonic motion executed by the piston, we can draw this like this, and this is the frictional loss, additional frictional loss. Similarly, this will be modified in this diagram also like this. Let us give a nomenclature Kg, and with the frictional loss this will be also the final diagram. Again I explain this. This is the constant delivery head at the beginning, again the acceleration of the piston which takes care of that, and it produces more head, that means this head is above this lift, this delivery side lift. Again the losses will be maximum when the velocity is here, maximum velocity is 0 at this two end, and again it is a deceleration and it comes here. So, the velocity, that is the discharge head, is little lower than this. This is because to take care of the distance, fluid is decelerated then, and this part of the fluid is in acceleration. So, therefore, in the delivery stroke also initial acceleration part gives greater head, that greater head has to be generated at the discharge end. Similarly, to take care of deceleration, the head generated will be little less. So, therefore, the head generated in the cylinder of the pump will be like this KPG. So, therefore, the final diagram from an ideal one which was a rectangle ABCD is changed to ELF. From ABCD is the ideal one, ideal, and ELF G P K E. This is either A, B, C, D, A we should write to complete it. This is actual in consideration of the inertia of the piston and the liquid, and at the same time the frictional losses. Now, after this let us consider the expressions for acceleration head. Let us consider the expressions of acceleration head. Now, let us consider the expressions of acceleration head. Expressions for acceleration heads. How to calculate these acceleration heads? Let me draw a picture first. Let this is the crank of radius r, and let this is the connecting rod which is sufficiently long L. Let this is given by x, and similarly this is x. Now, we derive an expression of acceleration in consideration of the crank rotation. Now, when L by R is very high, we can consider this as executing this, we can assume a simple harmonic motion executed by the piston due to the rotation of this crank with a uniform angular speed omega. Let us consider the rotation at some time from the inner dead center position, because this is the inner dead center position when the piston is here, when the crank is here. When the crank goes here, that means 180-degree rotation, then it goes to the outer dead, that means this is the outer dead. So, the outer dead to inner dead position is 2r, and this is known as one stroke. Okay. So, one stroke is completed when the crank moves from 0 degree to 180 degree. Okay. So, now if we consider at any time t the crank has made rotated at an angle theta with this direction axis, then if this is the displacement x, this is also x, that means the piston has moved from its inner dead center position to a distance x, which is given by this. So, this x can be written from here as r minus r cos theta. This is r cos theta and this is r, and theta is the angle for the constant angular velocity omega t. So, x is equal to r minus r cos omega t. Now, to find the velocity, we find the velocity of the piston. Velocity of the piston is equal to dx dt, which is equal to cos omega t minus, that is r omega sin omega t. Very simple. Then the acceleration of the piston, a piston, acceleration of the piston is equal to d v dt, derivative of this, and if we make this derivative d dt. Now, this is the I am extremely sorry, this is the acceleration of the piston is okay, but I think we will find out the acceleration of the pipeline. Acceleration of the piston will be definitely r omega square cos omega t. Now, we are interested the velocity in the pipeline, that means either in discharge pipe or in the suction pipe, inlet pipe. So, at any instant velocity in the pipeline and velocity of the piston is related like that, velocity in the piston times the cross sectional area of the piston and cross sectional area of the pipeline. That means, we use A as the cross sectional area of the piston and A is denoting the cross sectional area in the pipeline, maybe inlet pipe, suction pipe or delivery pipe. At any instant, because of the continuity for a steady flow means constant flow rate, volumetric flow rate, we can write this equation. So, therefore, we can write the V pipeline is equal to what? A by A from here, r omega sin omega t, and correspondingly the A pipeline that is acceleration. Here A is AS rather I give, that is the cross sectional area of the pipeline, rather I give AP rather. So, A by AP. So, therefore, acceleration will be d dt of this, that means A by AP r omega square cos omega t. As I told earlier that the velocity and acceleration at any instant between in the piston and the pipeline of the liquid in the piston, in the cylinder and in the pipeline, because in the cylinder it is that of the piston, in the cylinder in the pipeline is just varying by this area ratio because of the continuity. So, this is the velocity in the pipeline, this is the acceleration in the pipeline. Now, with this in mind that acceleration in the pipeline is this, we can write that the force now to create this acceleration in the pipeline, we require a force which is equal to this acceleration times the mass of the fluid. If you consider the mass of the fluid in the pipeline as this, where L is the length of the pipeline, that into this is of course AP r omega square cos omega t. So, ultimately it becomes AP will cancel. So, therefore, the force required to do this will be rho A L A by A, that means force required to accelerate the liquid mass will be A by A P r omega square. Okay, we may not write anything, straight we can write the pressure head caused. So, therefore, pressure head caused, this is the force required to accelerate the liquid mass either in the suction or delivery line. So, pressure is now caused by that force, that means which is known as acceleration head, which is known as acceleration head is nothing but this divided by A rho g, because force divided by area, this causes a pressure corresponding to acceleration, acceleration pressure divided by rho g. So, if you substitute this acceleration head H A, rather I write the pressure rate caused by the acceleration will become L by G A by A r omega square, again cos omega t I replace by theta. That means, this is force, this divided by A. A means again A P, sorry I forget, that means the area of the pipeline. So, this A P cancels, again one A P is coming. So, A by A P L by G, okay, this rho and rho cancels, r omega square I write cos. So, therefore, this is a very important expression relating to the acceleration head, because acceleration head can be found out for the liquid or the water, whatever may be in the piston, by using this acceleration. But usually the piston acceleration is neglected, velocity and acceleration as compared to the pipeline, because of the high ratio of this. Here A P is much less compared to the area of the cylinder. So, therefore, we are more interested in the acceleration head in the suction or delivery lines, delivery pipes, and this is the expression length L by G. L is the length of either suction or delivery pipe, and A is this area of the cylinder. A P is the area of the pipeline, which may be suction, which may be delivery, r omega square cos theta, theta is the crank angle. Okay. So, today up to this. Thank you.